There is another geography on Earth, one that exists between land and water, between atmosphere and ocean, and between solid ground and a frozen landscape that can move beneath our feet. The cryosphere is the part of the Earth system where water exists in its frozen state. Snow, glaciers, ice sheets, sea ice, permafrost, seasonally frozen ground. Together, they cover a substantial portion of the planet and influence far more than the regions where ice is visible. Frozen landscapes regulate the movement of water, reflect solar energy, store fresh water, shape coastlines and mountains, and influence global climate. For humans, they have always presented a particular challenge. Ice can support weight. It can preserve food. It can provide routes across otherwise impassable terrain. It can become a building material. But unlike stone or concrete, ice is never entirely still. It melts. It expands. It fractures. It flows. And in the coldest regions of the world, even the ground itself can freeze. Human settlement in these environments therefore required a different understanding of what it meant to build. Long before modern engineering, people living in cold regions had learned something fundamental. The environment was not simply an obstacle, it could be used. Snow, for example, contains a remarkable amount of trapped air. When compacted into blocks, it can form an effective insulating material. For Arctic peoples, snow architecture was not an attempt to defeat winter. It was an adaptation to it. The structure protected its occupants from the very environment outside it. But the more difficult problem appeared when permanent settlements expanded into regions where the ground remained frozen for years, decades, or centuries. Permafrost is ground that remains at or below 0 degrees Celsius for at least 2 consecutive years. It can contain soil, rock, ice, and enormous quantities of organic material. To the eye, it may look like ordinary ground. For an engineer, it is something very different, because frozen ground can behave like solid foundation material while it remains frozen. When it thaws, its mechanical properties can change dramatically. The ground can settle. Structures can shift. Roads can deform. Pipelines can bend. And buildings designed for stable terrain can begin to move. The challenge was therefore not simply how to construct in the Arctic. It was how to construct without changing the thermal conditions that made the ground capable of supporting the structure in the first place. That problem became increasingly important during the 20th century. As governments, industries, and military organizations moved deeper into northern territories, permanent infrastructure followed. Roads, airfields, mines, railways, pipelines, towns. The frozen landscape was becoming an engineered landscape. In Alaska, Canada, Greenland, and other high-latitude regions, engineering has had to account for a landscape whose stability depends partly on temperature. The result is a distinctive form of infrastructure. Pipelines are elevated where necessary. Buildings stand above the tundra. Roads are constructed with carefully controlled layers of fill. Airfields require constant monitoring. Some foundations incorporate cooling systems. The objective is not to freeze the entire landscape. It is to preserve the specific conditions on which critical infrastructure depends. This represents a significant shift in human engineering. For thousands of years, construction largely assumed that the ground was stable. In permafrost regions, stability itself became something that had to be engineered. For decades, the engineering problem appeared manageable. Then the climate began to change. Across much of the Arctic, temperatures have risen faster than the global average. The consequences extend beyond the surface. As permafrost warms and thaws, ground that once behaved as a stable foundation can lose strength. Ice within the soil can melt. The resulting water can drain away. The ground can settle. For infrastructure built upon it, the effects can be gradual and difficult to see at first. A small change in elevation can place new stresses on a building. A road surface can develop waves and depressions. A pipeline can experience changes in support. Entire communities may face increasing maintenance costs, and the problem extends beyond engineering. Permafrost contains vast stores of organic carbon accumulated from plants and animals over thousands of years. When frozen ground thaws, microorganisms can begin decomposing this material. Carbon dioxide and methane can be released. The frozen ground therefore becomes part of the climate system itself. A warming climate can destabilize permafrost. Thawing permafrost can contribute additional greenhouse gases to the atmosphere. The result is a feedback between climate and frozen ground. Human infrastructure sits directly within that feedback. The same warming that threatens the foundations of northern communities is also changing the landscape around them. Lakes can form where ice-rich ground collapses. Drainage patterns can change. Vegetation can shift. Wildfires can remove insulating layers of vegetation and organic soil, allowing additional heat to penetrate the ground. The Arctic is not simply becoming warmer. In many places, its physical geography is changing, and infrastructure designed for the 20th century Arctic is being tested by a 21st century climate. The future of building in the cryosphere will not be determined by construction technology alone. It will depend on whether engineers can continuously measure a landscape that is itself changing. Sensors can now monitor ground temperature at different depths. Satellite radar can detect millimeter-scale changes in the elevation of surfaces. Remote systems can track deformation across roads, buildings, and pipelines. Computational models can combine these measurements with climate projections to estimate where permafrost is most vulnerable. The Arctic is becoming an increasingly instrumented landscape. That creates new possibilities. Buildings could be designed with foundations capable of adapting to changing ground conditions. Roads could incorporate materials and drainage systems designed specifically for thaw-sensitive terrain. Cooling systems could respond automatically to ground temperatures. Infrastructure corridors could be planned around areas where long-term stability is most likely. Some construction may become modular and relocatable. Rather than assuming that a building will remain in one place for a century, future settlements may need to anticipate movement. The principle is fundamentally different. Instead of constructing for a fixed climate, infrastructure may need to be designed for a changing one. But the cryosphere also presents opportunities beyond adaptation. The polar regions contain enormous potential for scientific research. They provide natural laboratories for understanding climate, geology, ecosystems, and the history of the planet. They may also become increasingly important for communications, transportation, energy infrastructure, and resource development. Yet every new opportunity brings the same question. How much infrastructure can the cryosphere support without accelerating the changes already underway?
There's a line where the old world ends. I stood there once, I won't again. Footsteps lost in...
For much of human history, the frozen regions of the planet were places to survive. Then they became places to build. Now they are becoming places where the future of construction itself is being tested. The lesson of the cryosphere is not simply that cold environments are difficult. It is that the assumptions behind conventional construction do not always apply. Ground can move. Foundations can depend on temperature. A landscape that appears permanent can change within a human lifetime. The challenge ahead will therefore require more than stronger buildings. It will require a different relationship between infrastructure and the environment that supports it. Future structures may need to monitor their own foundations. Cities may need to map the thermal behavior of the ground beneath every neighborhood. Roads may need to be designed as adaptive systems rather than permanent surfaces. Critical infrastructure may need redundancy, relocation strategies, and continuous environmental monitoring. And in some places, the most rational engineering decision may be not to build at all. That may be the most difficult lesson of the cryosphere. Humanity has become extraordinarily capable of overcoming physical obstacles, but engineering can change the environment it is designed to overcome. A road alters drainage, a building alters ground temperature, a pipeline fragments the landscape, a cleared surface can accelerate thaw. The infrastructure that connects a remote region to the wider world can also become part of the forces transforming that region. The future will therefore not be defined simply by whether humans can build on frozen ground. We already can. The question is whether what we build can remain viable as the ground changes beneath it. The cryosphere is not a static landscape waiting to be conquered. It is part of a planetary system. Ice reflects sunlight. Snow stores water. Glaciers shape mountains. Sea ice influences the oceans. Permafrost stores carbon. Frozen ground supports communities, roads, pipelines, airfields, and entire settlements. And all of these functions are connected. For centuries, humans learned to read the frozen landscape. Then we learned to engineer it. Now we are beginning to understand that the landscape is changing faster than many of the structures built upon it were designed to anticipate. The next generation of Arctic architecture may therefore have a different objective, not to dominate the ice, not even simply to withstand it, but to operate within a landscape that is constantly changing. Because the future of building in the cryosphere will ultimately depend on one principle. The strongest structure is not necessarily the one that resists the environment. It may be the one that understands it.
There's a line where the old world ends. I stood there once, I won't again. Footsteps lost in endless white, no direction left to fight. I carved a place I thought was safe, built it out of cold and faith. Now every wall just echoes back a quieter version of what I lack, and I have been holding tight to something fading. Under the ice cap I keep it still, all of the fire I never let spill. Frozen in lakes no one can see what I was, what I couldn't be. Under the ice cap time moves slow, holding the things I won't let go. If it all breaks, if it all cracks, would I survive?